So my name is Franck Pereira Dos Santos, and I work at SYRTE, at the Paris Observatory. And I'm the PI of the SYRTE team in the project. I'm a research director at CNRS. We at SYRTE actually, we are experts in the design, the building and the metrological evaluation of the performances of atomic sensors based on atomic interferometry. So we do lab instruments which are really static and which are aimed to reach the ultimate performances that this technology allows for. And that puts us in a good position to actually extrapolate the level of performances of these sensors when applied outside the lab for mobile applications, and in particular for space applications of the technology. Well, in principle, this atomic accelerometer we build is not that different from any accelerometer of any other technology. I mean, the very principle is just that we do the measurement of a test mass with respect to a frame. In our case, this test mass is a cloud of atoms which are free-falling with respect to the body of the experiment. And what we do is we try to precisely measure this displacement of the free-falling atom with respect to this body frame. Atom interferometry is somewhat specific in the fact that we actually use the lasers to monitor this position. So these lasers are like the very fine rulers that we use to track the motion of the atoms, and we benefit from the fact that it's like a ruler with a very fine step, which is given by the wavelength of the light. So it's micrometer scale, and we can even split this micrometer small division into like thousands of subparts, and we can track the position of the atom with respect to this very fine ruler. So that makes this technology extremely sensitive in tracking the motion of the atoms, and that's what makes it good for space applications in particular. Well, as other technologies, actually, space offers the possibility to probe the motion of those free-falling objects over very long time scales. Since if we do accelerometry on the ground, we just drop a system and it falls, and we can only observe it for a fraction of a second, otherwise it moves by meters. And when putting this atomic accelerometer in space, basically this free-fall mass that we use falls, but together with the satellite. So its position remains basically at the center of the satellite, and we can then observe it for a very extended, long times of several seconds or so, which is somewhat impossible to do here on the ground because it would fall for like tens of meters, if not more. So, and that is key actually for the precision in the end of the measurement of the acceleration, that we can look at this motion over a very long time scale. The longer the time scale, the longer the time we observe the motion, the more sensitive we are in the measurement of the small acceleration.